Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 5, Advanced Mechanics. This is the start of the Year 12 Physics syllabus. We are going to go through Inquiry Question 1, Projectile Motion, and with focus of this particular dot point. You can see there are 3 inquiry questions in total for Module 5. So when we talk about projectile motion, it's all about how things are transjected. So imagine if you throw an object, imagine you throw a ball. So imagine if you're this person here and you throw a ball, there's quite a lot of different things we can look into. So an example of trajectories is just you throwing a ball. It could be the drop of a bullet. There are many things that can affect how the object will fall, mainly gravity. We can use kinematic equations to work out how fast it will fall. So what's the time it takes for it to fall? What's the velocity in which it reaches? What's the acceleration that causes it to drop? And it can tell us a lot of different things. It can tell us how long it's going to be in flight for, what's the speed in which it was launched, what angle did we launch it at. So there's quite a lot of different calculations that can be conducted using projectile motion. So our lesson intention today is just to define what projectile motion is, and the success criteria is to analyze a projectile motion based on its horizontal and vertical components. The reference that you'll need for the textbook is right here. Let's begin. So just a bit of context of how falling works, or how people interpreted falling. Originally it came from the idea from Aristotle, the concept of things will try and reach its original state. So say, for example, a cannonball. The reason why a cannonball would fall down, according to Aristotle, was because it was naturally an earth object. Okay, so the reason why the cannonball fell down was it was an earth-like element, and so once it's used up its sort of what they call energy in a way, used up all the violent motion it has, it will eventually fall back down to earth. That's the interpretation at the time. That was later on changed a little bit in the, I think it was Ptolemy, or somewhere around the Middle Ages. So late Middle Ages, about 1500s AD, they come up with this concept of impetus. So instead of the object, once it has some violent motion and then just abruptly ending and falling straight down like you have with Aristotle here, you can see there's sort of a little mini curve here, and then the object just kind of falls directly down. Now, obviously, what you can imagine is if you fire a cannonball, it doesn't actually create these kind of trajectories. But if you think about it quite clearly, the reason why they assumed it was this kind of motion is to do with air resistance. Now imagine you have really strong air resistance when you throw an object forwards. All right. Without air resistance, the ball should usually follow a nice parabolic shape. With air resistance, the object will kind of curve down a bit sooner. And if you have a really strong air resistance, it will look like it fell directly down. So that's kind of the understanding that the medieval scientists or the ancients had of falling objects or projectile motion. So with Aristotle's canon, just give you a bit more context, it starts with this concept where you push an object, causing it to have some unnatural violent motion. This motion is in a straight line. When the unnatural motion is exhausted, the natural motion will take over. What we mean by the natural motion is where the object originally belonged to. So say if we have an earth-like material, the reason why we call it earth-like elements is because, if you recall, Aristotle had 4 elements: fire, earth, wind, and air. So there's that. And so once that Earth element has used up all the unnatural motion, it's going to go back to its resting place. So this looks like something along the lines of this. So you can see when you fire an object out of the cannon, it is going in that particular direction, and then according to Aristotle, once it's run out of that violent motion, it just abruptly drops down. Now, you and I know that that's not really how the world works, so obviously there must be some other explanation of what's going on, and a better one too. Another thing that Aristotle got wrong back in the day, and mind you, this was about 400 BC, so there's a lot of changes happening there. Aristotle's view was mass would affect how fast an object drops. Now again, one of the reasons why that could be the case is because of air resistance. But what we actually know is all objects will accelerate on Earth and anywhere in the universe at the, well, I'll rephrase that, any object that is dropped on Earth, be it at the same height, so assuming that they're dropped at the same height, they will fall at the same rate. So they're both going to be accelerated at the same rate of gravity. And obviously the value for gravity on average is 9.8 meters per second squared. That's the acceleration that all objects will experience. Unlike what Aristotle said, that the larger object will accelerate further down because of mass. Mass actually has nothing to do with falling down. Okay, and then we move to the 1500s, and that's when we develop an idea called impetus. Impetus, again, we're still on the lines of believing that weight and velocity had something to do with things falling. So impetus is, let's just give a bit of context. So the initial stage when you launch an object, it moves in a straight line motion, you can see here, in line with the impetus. During the intermediate stage, so this is our intermediate stage, gravity recovers and air resistance slows the projectile, and then the path begins to deviate into a curve like so. And then the final stage, the impetus is spent. You can sort of think of impetus as maybe, so to put, energy in a way. Not exactly how they saw it back in the day, but that's sort of how you can quantify what they were thinking. And once the impetus was spent, it just fell directly down. So those were all the different ways we thought of how you could launch an object and how things fell back in the day. That was obviously changed when a guy called Galileo Galilei came in and did a couple of experiments. Now, you might have known the so-called tale of him trying to drop a feather and a cannonball down the Tower of Pisa. That didn't really happen, mainly because of air resistance again. But he did find the fact that things would fall at the same rate regardless of their mass. So it shouldn't be weight, because weight can be interpreted as force, but technically we're talking about, in this case, mass of object. So he had to develop a different way to demonstrate how things fell and how fast things fell in relations to their mass. So he developed an experiment known as projectiles, and he found a way that these projectiles would sort of fall like a parabola. So if you see this here, so one way to picture it, imagine this is a table. So here's my table, and I have a sort of metal ball running along this table here. Now, depending on how fast this ball is running along the table, Galileo found that the ball would drop at a different horizontal displacement, like that. But it maintained this sort of semi-parabolic shape. You can sort of see it in this diagram of his recordings. That's this kind of curves he saw there. So from that, he worked out one important feature, and that's the horizontal and the vertical components are independent of each other. So what we mean by that is how fast the object is falling down, what we call the y motion, is completely independent of how fast the object is moving horizontally. Okay, we'll explain exactly why we can work that out based on the parabolic shape a little bit later. So we'll talk about that. You can also see what we talk about in terms of the motions. So say if you're on a boat and the boat is moving in the right-hand direction, you drop the ball directly down. Now what he actually found was, although you're the person moving on the boat, whatever object you're holding on to also has the same speed as you, okay? So if you're traveling at a constant speed, you drop the ball directly down, so you don't add any force, you just let it go. To you, it looks like it fell directly below, but by a bystander's perspective, the ball's actually traveled in the same direction at the same speed, horizontally speaking, assuming that's where the boat is moving, to you. This is also known as frame of reference and a bit of relativity. So the actual experiment that Galileo performed looked a bit more like this. Now it looks like more like an inclined plane, as you can see there. Change to the laser, so you can see it's more like an inclined plane. Part of the reason why he did the inclined plane experiment is because he can actually control how much acceleration due to gravity is placed on the ball. You can see that this is at an angle to where the gravitational force is. Gravitational force would be coming directly down, but if you put it at an angle, the effects of gravity would be smaller, so it's easier to sort of measure in between. If we look at the overall design, he rolled a bronze ball down an inclined plane and he tried to look at the parabolic path. Now, assuming that he placed the different mass spheres on the same starting point at the same angle, rolling the spheres down, both balls, assuming the really large one, so one with really high mass and one with really low mass, would reach the bottom of the plane at the same time, regardless of how heavy they are, so long as they started at the same position and obviously the inclined plane was at the same angle when the experiment was performed. So that was his main discovery there. Okay, so when it comes to demonstrating projectile motion, and I'll do another video for you to see, this is going to be using the PhET simulation. But what actually happens is when you launch a projectile, and we are making one big assumption here, assuming no air resistance. Think about it this way. If I have a cannonball that gets launched at an angle of 40 degrees, as you can see here, it's going to have two sets of motion. One motion of it moving up and one motion of it moving across. That kind of explains this starting point here. Okay, this sort of shows why it goes at an angle. You've seen this when we talk about resolving two perpendicular component vectors into one. So that's where the diagonal component comes from. You can sort of see that the height of this motion begins to plateau and then reach a peak. What's actually happening here is due to the acceleration of gravity. Okay, call it little g. So what's actually happening is gravity is acting at the same rate throughout this motion. I'll do it in a different color just so we don't get confused with it. So we use red. So gravity is acting at the same rate throughout this motion. So if we launched our object upwards, it is going to lose a little bit of speed over time. So let's say it's going up here, has a lot of speed, and then as gravity does its work over time, the ball is pushing against gravity to the point where there's not much speed left of it pointing up this way. We'll call this the uy, so the original velocity here, and then it reaches this point here where the velocity of the y component is equal to 0. And then, as you can see, after this point, the cannonball, our fictional cannonball, begins to fall down. And the reason why is because it's gaining speed in the y component, but in the opposite direction from what it originally was. So you can see it's falling and falling and falling down, to which this point here we have, which will be its final velocity. So that kind of explains why it kind of goes up and goes down, because there's a change in the speed in the y component, or the direction of the speed as well. Let's say velocity, more correct. Okay, so there's that. Now if I change my color, hopefully try orange, you can see the trajectory is continuously moving forwards. If you actually look very carefully, the distance between each interval, at least horizontally, stays the same. So if I just sort of make a drawing of all the different gaps, the distance of the gaps, they actually stay the same throughout the whole thing. And what we can actually conclude from that is, assuming there is no air resistance, there is nothing causing any acceleration on a projectile when it's moving in the x component. Okay? So what we can say is the original velocity when you launch a projectile is always going to equal the final velocity of the projectile over here when we're talking about the horizontal component. If we're talking about the y component, it's not going to be the same, particularly if one is going up and one then goes down. So there you have it. That's what we can tell from projectile motion. And this can only happen if the horizontal component and the vertical component are moving independent of each other. Otherwise, you wouldn't see a parabolic shape like this. And for those who ask, what about if it was air resistance? Then obviously the horizontal component will get smaller over time, but we don't look at that in HSC physics. Just another little analysis of each of these motions. So imagine we look at this frame by frame. So imagine each frame is about 1 second. So time 2, time 3, something along the lines of that. You can see for the vertical motion, the distance traveled by this tennis ball here gets smaller and smaller. And the reason why the displacement or the change in displacement gets smaller, at least in this scenario here, is because the velocity is also decreasing. Whilst on this case, we have an increase in the displacement, negative displacement we'll call it. Actually, I'll write the negative out in front. And that's because the negative velocity change is increasing due to being work done by gravity. You can see the horizontal motion stays the same throughout. So this velocity here and this velocity at this point here will be equal to each other. You can see it again here with another perspective of this diagram. So there's that. So what can we conclude about Galileo's ideas of projectile motion? One is that the horizontal and vertical components are directly opposite to each other. So they are independent of each other. Okay. We also know that the vertical motion is influenced by gravity only, and anything falling is not related to the mass of the object. The horizontal motion will have a constant velocity, make that very clear. So we'll have a constant velocity The reason why it has a constant velocity is because there is no acceleration being applied or experienced, and that's because we ignore air resistance. Okay, so that's Galileo's conclusion about projectile motion. So thank you so much for watching the first part of this video. I'm going to also link you to another video that explains, looks at a past paper question that looks at Galileo's analysis of projectile motion. Another video I'll also do is some calculations related to projectile motion to get you started. So thank you for watching this video. I'll see you in the next one.